Welcome to this NPTEL course on Dynamics and Control of Mechanical Systems. My name is Ashitava Ghoshal. I am a professor in the Department of Mechanical Engineering, also in the Center for Product Design and Manufacturing, and in the Robert Bosch Center for Cyber-Physical Systems, Indian Institute of Science, Bangalore. In the last week, we had looked at position and orientation of a rigid body and combined motion of a rigid body consisting of translation and rotation. In this week, we will look at the velocity and acceleration of rigid body in 3D space. In this lecture, we will look at the motion of rigid bodies and particles. To recapitulate, in the last lecture, we looked at the position of a point on a rigid body in 3D space, and this is represented by a vector with three components, and the linear velocity is the derivative of the position vector. The orientation, on the other hand, is described by a matrix, a 3x3 matrix, and the angular velocity is derived from the derivative of the rotation matrix. And we saw there are two kinds of angular velocities. One was the body fixed and one was the space fixed. So in order to obtain the angular velocity, we first obtained a skew-symmetric matrix, which is R dot R transpose. And this led to the concept of a space fixed angular velocity vector A omega with a superscript S. We also showed that you could obtain a skew symmetric matrix from R transpose R dot, okay, and this leads to the notion of a body fixed angular velocity vector, which is denoted by A omega B with a superscript B. So this S and B basically denotes that one of them is a space fixed angular velocity vector and one of them is a body fixed angular velocity vector. And I showed you that both are related. They are related through the rotation matrix ABR. The angular velocity of a rigid body can also be obtained from the three Euler angles. Okay. So they are not exactly the straightforward derivatives of, let's say, theta 1, theta 2 and theta 3, which are the three Euler angles, but they are related with cosine and sine of the angles also. In this lecture, we'll look at the general motion of a rigid body. Basically, we will combine the linear and angular velocity together. So the figure shows a fixed or a reference coordinate system A with xa, ya, za and the origin OA, and we have a rigid body in which we have fixed another coordinate system given by xb, yb, zb and the origin OB. So any point on this rigid body, this point can be located with reference to the xb, yb, zb coordinate system by this vector bp. The location of the origin of this coordinate system attached to the rigid body is given by AOB, and we can also find the same point with respect to the A coordinate system. So basically A of P is nothing but the vector addition of these two, but we need to be careful and add it properly. The important thing in this figure is that the origins of B, OB and the origin OA are not coincident. So there is a rotation matrix associated with this rigid body. So this is the rotation matrix B with respect to A, and we have looked at various ways of representing the rotation matrix. So for the moment we assume that there is a rotation matrix which is available. So as I was telling, that this vector AP can be written as AOB plus this vector, but pre-multiplied by ABR. Why? Because we need to make sure that both the vectors are in the same coordinate system. And as I mentioned earlier, AOB locates the origin of the B coordinate system with respect to the A coordinate system, the origin of the A coordinate system OA. We now look at the derivative of this vector AP. Okay, so we can take this expression AP is equal to AOB plus ABRBP, and we take the derivative of both sides with respect to time. So let's go over slowly. The derivative of AP will be denoted by AVP. V means the velocity. P means this point P. So first term is the derivative of this AOB. So this is given by the velocity of the origin of B coordinate system with respect to the A. So this is this vector. Then we need to use chain rule. So the first term is d by dt of this rotation matrix into BP, and then ABR into d by dt of BP. Okay. So let's just simplify. So the first term remains same, but this derivative can be written in this form. So we have ABR dot, which is denoting the derivative of the rotation matrix. But then instead of writing BP, I can write AP in pre-multiplied by ABR transpose. Okay, so you can think of this as BA, and then this AA will cancel, and then we are left with BP. And the last term, let's leave it at the moment in this form. So what you can see is this quantity, which is R dot R transpose, is nothing but the space fixed angular velocity of this rigid body, okay, B with respect to A. So simplifying, what we can show that this velocity vector of this point is nothing but the velocity of this origin plus something like omega cross R, which you have seen in many undergraduate mechanics courses, plus this derivative of this BP and then pre-multiplied by rotation matrix. Okay, so this is a very useful and important formula which tells you that the velocity of a point on a moving rigid body, which is also translating and rotating, is given by three terms. One is the velocity of the origin, one is something like omega cross R, and one is the velocity of the point itself in the moving coordinate system B. So this is just to repeat, the velocity of a point is nothing but the velocity of the origin plus some d by dt of R into BP plus ABR into d by dt of BP. So we can also pre-multiply this velocity vector by BAR. Okay, so BAR, so this again the A and A will sort of cancels in your mind. So we are left with the velocity of this point P in the B coordinate system, described in the B coordinate system. So if you go through the process, then you have BAR into AVOB, then ABR transpose ABR dot into BP plus d by dt of BP. So remember ABR and then pre-multiply by BAR, we left with the identity. So this is the simplified expression. So this is the velocity of this point P described in the B coordinate system. Okay. Again, remember this is the velocity of the origin of point P in the moving frame respectively. So now if you carefully look at this expression, what you can see is this is like R transpose R dot. Okay, ABR transpose ABR. This we have seen earlier is the body fixed angular velocity vector of B with respect to A. So here is that B superscript which tells you that this is the angular velocity vector in the body coordinate system. Let's continue. The angular velocity and the linear velocity can be again differentiated to obtain linear and angular acceleration. Okay, so we will start with angular acceleration because that is sort of simple. So the angular acceleration of a rigid body with respect to the A coordinate system is nothing but the derivative of the angular velocity with respect to time. Okay, remember angular velocity is a vector and we can take the derivative of each components of the vector and get the angular acceleration. Okay, it is simpler than when we went from rotation matrix to angular velocity, because now we are dealing with vectors. A little bit of useful relationships. So one very useful relationship is that R dot R transpose is what we have seen is the right skew multiplication, and this is the skew symmetric matrix. So A B R dot, if you can simplify, if you post multiply, then you can show that this is nothing but this right skew symmetric matrix into ABR. Okay, so post multiply by ABR, so you will get ABR dot, which is what is left. This into matrix itself is identity, and this right hand side is omega into ABR. Likewise, another useful relationship is this R dot into BP, ABR R dot into BP is written, can be written as omega into ABR into BP. Okay, so this is also nothing but AB omega R into AP. So this is the space fixed angular velocity vector. So this is like A omega B cross AP. Okay, so important thing is this R dot into BP is same as A omega B into A cross or product with AP. So let's continue. So we had this linear velocity vector of a point on the rigid body B given in this form, which was the velocity vector of the origin plus some R dot into BP plus ABR into BVP. So this is nothing but d by dt of the position vector in the body coordinate system itself. It is d by dt of BP. So if you differentiate both sides again with respect to time, so the derivative of the velocity is the acceleration of the point. The derivative of this velocity of the origin is the acceleration of the origin of the B coordinate system, and then this term will come, we'll get several terms from here. So again we need to take the derivative of the first term into this plus this into the derivative of this. So basically we have to use chain rule here. We also have to use chain rule here. Okay, so from this term and this term, so there are 4 terms here. So you can reorganize these 4 terms, and then what you can see is you will get one term which is A omega B dot. So this is like alpha. This is like angular acceleration into ABR into BP. So one of the term is this. The second term is that A omega B cross ABR dot into BP, and there is also these 2 terms. Okay, so what you can see is there are 1, 2, 3, 4, 5 and one more 6 terms which appear from this. Okay, this we can simplify using these relationships which I told you, that ABR dot BP is A omega into ABR into BP. We denote the derivative of BP as BVP, the second derivative as BAP, and this ABR dot BP is ABR, we can also dot into ABR transpose ABR into BVP. So you will get A omega B cross ABR BVP. Okay, so think about a little bit. It is nothing but simple chain rule and using the derivatives, and also making sure that we understand what is the derivative of a rotation matrix. Okay, so once more, so the derivative of the left hand side AVP will give you the acceleration of the point in the A coordinate system. The derivative of the origin will give you the acceleration of the origin, and then from these 2 terms we have something which is alpha times some distance. So remember from undergraduate we have a tangential acceleration which is alpha times r. Then we have something which is A omega bs into this, and one more this, and then this is the last term is also very well known. This is nothing but the acceleration of the point in the B coordinate system itself. Okay. So what you can see here is there are two terms which are sort of similar. One is this one, which is ABR into d by dt of BP, and then there is one which is ABR dot into d by dt of BP. So these two terms are sort of similar, and we'll see later that this gives rise to something which is known as the Coriolis acceleration. Whereas this term here, it is omega cross some derivative of the rotation matrix into some distance. So this is like omega cross r. Okay, this is the centripetal term. So as I said, we can regroup all these expressions, and then we can see that the acceleration of the point P is the acceleration of the origin plus some alpha times r plus some omega cross r. This is the centripetal term. Then there are two of these terms. As I said, they are sort of similar, and which you will get 2 omega cross some relative velocity ABR into BVP. This is the velocity of the point in the B coordinate system, and this is the acceleration of the point in the B coordinate system. So there are 1, 2, 3, 4, 5 terms in the acceleration of a point in the A coordinate system when this rigid body is moving, translating, as well as it is rotating. So just to recapitulate, we have this expression for the acceleration of this point P with respect to the A coordinate system, that is given by the acceleration of the origin OB, which is AOB, this term. Then we have this term which is the tangential acceleration. This is determined by the rate of change of the angular velocity into some distance. Then we have this term which is omega cross r, which is called as the centripetal acceleration. Then we have one more term which is the Coriolis acceleration, which is omega cross v relative. And then finally acceleration, which is this term of the body of the point P in the B coordinate system itself. So let's look at an example, and this is a very classic and simple example. What we have here is a disk which is rotating with omega and omega dot, or omega and alpha, and there is an ant which is moving on this disk. Okay, so we define a few coordinate systems. One is this 0 coordinate system, which is x0, y0. This is the fixed or the reference coordinate system. Then we have another coordinate system which is 1, which is fixed to the rotating disk. Okay, so you can see it is rotated by some angle θ1 and x1, y1, o, but the origins are at the same place. So we can obtain the rotation matrix of this one coordinate system, this one coordinate system with respect to the 0 coordinate system, and that is very straightforward because it's a planar rotating disk. The rotation axis is about the z axis, which is coming out. So you have cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. This is one of the simple rotations about the z axis. The angular velocity of the disk, as I said, is omega. So it is 0 omega 1 into 0, 0 theta dot. So this omega is nothing but theta dot, same as this theta which is shown here. The angular acceleration, which is denoted by alpha, okay, so of this rotating coordinate system 1 with respect to the fixed coordinate system 0 is 0, 0 theta double dot. The location of this ant, okay, in the coordinate system 1 is along the x-axis. This is just for simplification. It could have been anywhere else. So what we have is this position vector of this ant in the one coordinate system is L00. Okay, it's a column vector with only x component, which is L. The relative velocity and acceleration of the ant in this one coordinate system is again assumed for simplicity that it is along the moving x-axis. Okay, so the v relative has only an x component, which is v relative 0, 0, and the acceleration of this ant in this rotating coordinate system is also along the x-axis, a relative 0, 0. Okay, these are just to simplify the algebra and the terms which will appear. So let's continue. So the position of this ant in the 0 coordinate system can be obtained by pre-multiplying 1p into 0, 1r. And if we saw what is 0, 1r. It was a simple rotation about z-axis. So you will end up with L cos theta, L sin theta 0. So that is sort of obvious. So you can see that this is L, this distance is L. So along the x0 axis, it is L cos theta. Along the y0 axis, it is L sin theta. Okay, and there is no z component because all the motion is happening on the rotating disk, which is a planar rotating disk. If you take the derivative of both sides of this one and this one, so the derivative of the position vector is the velocity of this ant, and that can be written as omega cross r plus the velocity of the ant itself. Okay, and we need to make sure that we add these two vectors in the right coordinate system. So we have to pre-multiply here with a rotation matrix and here also with a rotation matrix. So remember 1p was L00, 0, so 0, 1 into 1p, and then omega cross this will give me some term which is minus L sin theta theta dot, and the y component will be L cos theta theta dot, and then this term here, which is v relative along the x1 axis in the origin in the 0 coordinate system, will be v rel cos theta and v rel sin theta. Okay, so this is the velocity of the point looked at from the 0 coordinate system as described in the fixed or reference coordinate system. We can again take the derivative of this, which will give us the acceleration. So in the last slide, I had shown you that there were 5 terms in the acceleration. Okay, so the same thing is here, except one term is not there. The origin of the 2 coordinate systems are at the same place. Okay, so the AOB is not there, but the tangential acceleration is there, the centripetal acceleration is there, the Coriolis acceleration is there, and the acceleration of the ant itself in the 1 coordinate system is also there. So again, we see that we can evaluate these terms because alpha is nothing but 0, 0 theta double dot. Okay, omega is 0, 0 theta dot. We know what is 1p, we know what is the rotation matrix, we also know what is omega here, and we know what is vp. 1 vp is nothing but v rel 0, 0, and 1 ap is nothing but a rel 0, 0. And then when you pre-multiply by a rotation matrix 0, 1r, you will get some a rel cos theta, a rel sin theta 0. Similarly here, this Coriolis term 2 omega cross v rel, you will get minus v rel sin theta into theta dot, and then v rel cos theta into theta dot and 0. The centripetal term is minus L cos theta theta dot square, L sin theta theta dot square, and 0 again. All the z component of everything is 0. And the tangential acceleration is minus L sin theta theta double dot, L cos theta theta double dot. Okay, so this is a very straightforward example which you may have seen in your undergraduate. I'm just trying to show you that we get exactly very similar results, but now with this different notation. And basically we are trying to use the notion of a rotation matrix and how it is body fixed and space fixed angular velocity vector and accelerations and so on. Okay, so this is a different systematic way of deriving or solving the problem of this ant, which you might have done earlier. So all these acceleration terms we can also obtain in the 1 coordinate system, basically in the rotating coordinate system, the coordinate system which is attached to the rotating disk. So in some sense, we need to pre-multiply by a rotation matrix. Okay, so we need to transform from 0, 1, okay, so the 2 by pre-multiplying by 0, 1 transpose, or okay, which is also same as 1, 0. So the position vector was given as this 0, 1 r 1 p. The velocity vector was given by derivative of this expression, which is d by dt of r, and then 1 r into d by dt of p. Okay, so if you pre-multiply both sides of this equation by 1, 0 r, so you have 1, 0 r into 0 vp. This is nothing but the velocity of the point in the one coordinate system. Again, in your mind, you can think of this 0 and 0 will cancel, and you are left with 1. So then if you pre-multiply 1, 0 r, okay, to the right side, then you will get some r transpose r dot into 1p, and this last term will be just d by dt of 1p. Okay, so what is this r transpose r dot? This is the body fixed angular velocity matrix. Remember, space fixed was r dot r transpose, whereas body fixed was r transpose r dot. Okay, so hence the linear velocity of the point P described in the moving coordinate system or the rotating coordinate system is omega b cross 1p plus v relative. Okay, so v relative is what? It is just x component. So v rel 0, 0. And similarly, what is 1p? It is L 0, 0, and omega b is 0, 0 theta 1 theta dot. Okay, so we can evaluate both the terms on the right hand side, and we can get this velocity of the point in the one coordinate system. So continuing with this ant on a rotating disk example, the velocity of this ant in the one coordinate system is given by this rotation matrix. It is nothing but r transpose into the linear velocity component, which is minus L sine theta theta dot plus V rel cos theta L cos theta theta dot plus V rel sine theta 0. So if you simply multiply these two, this matrix into this vector and simplify, you will get V rel L theta dot 0. So it makes sense, right? Because if you are in this rotating coordinate system, the velocity of the ant will be clearly along the x-axis, and due to the rotation we have some L theta dot term. Similar to this velocity vector in the one coordinate system, we can also obtain the acceleration of this point in the one coordinate system, and that again in some sense we need to pre-multiply the acceleration vector in the 0 coordinate system with the 0, 1 r transpose. So if you do the algebra and simplify, you will see that the acceleration of this ant in the one coordinate system has 4 terms: 1, 2, 3 and 4. Okay, so we have one which is alpha times r, which is 0, 0 theta double dot is the angular acceleration, 1p is the position vector in the one coordinate system. Then we also have this Coriolis term, which is this one actually, and then we have a centripetal term which is omega cross r, and then we have this acceleration of this ant in the coordinate system 1. So that is nothing but a rel 0, 0. We assumed that the ant was traveling along the local or the rotating x-axis. The Coriolis and the centripetal term has this 0 omega b. So this is nothing but r transpose r dot. This is derived from that skew-symmetric matrix, and we remember it was the body fixed angular velocity vector. So if you multiply all this omega cross r and 2 omega v rel, and then we do all this algebra and simplify, we will get a acceleration vector in the one coordinate system of this form. So one is minus L theta dot square plus a relative Then you have L theta double dot plus 2 theta dot V rel. This is the Y component. Previous one was the X component, and the Z component is 0. Okay. So what you can see is this, and there is an acceleration towards the origin, and then there is an acceleration of the ant going away from the origin. So that is the X component. Then we have this L theta double dot, which is the tangential acceleration, but this is the other term, which is the Coriolis term, which is acting along the Y direction. So in summary, we have a centripetal acceleration, which is minus L theta dot square. We have a tangential acceleration, which is L theta double dot. Then we have a Coriolis acceleration, which is 2 theta dot V rel. So I'm sure many of you would have seen similar expressions in your undergraduate mechanics, but again, the whole idea is that we want to do it in a nice, systematic, formal way. Okay, and we show that how the space fixed and body fixed angular velocity vectors appear. Next, we look at a purely numerical example of obtaining the linear and angular velocities, linear and angular accelerations of a rigid body which is rotating as well as translating. So the picture is here. We have this rigid body which is with a fixed coordinate system B, which is attached to the rigid body. We have a point on this rigid body, and as before, the vector locating the origin of the B coordinate system is given by AOB. This point on the rigid body is given by BP, and so on. So we are going to choose these functions of time arbitrarily. Okay, so just there's no particular reason why AOB as a function of time is chosen as sine t x component, y component is t cube minus 3t, z component is 1 minus sine t cos t, and so on. It is just to show that given a function of time for all these quantities, how the body is translating and rotating, we can find what are the terms of the angular velocity, linear velocity, angular acceleration, and linear acceleration. Okay, so the point P in the B coordinate system is also changing as cos t x component, t square minus 3t is the y component, and z component is 1 minus sine t cos t. So as I have said, this is chosen arbitrarily. We are also going to represent the orientation of this rotating rigid body using x, y, z body fixed Euler angles. Okay, so we have a rotation about x given by theta 1 as a function of time, rotation of theta 2 about moving y, which is theta 2, and rotation about the moved z, which is 8t minus 10. Again, these functions of time for theta 1, theta 2, and theta 3 are chosen arbitrarily. So given this initial set of data, at t equals 0, we can find the position vector. So how do I find the position vector? It is nothing but this vector plus this vector and pre-multiply by the rotation matrix. So I can find what is the rotation matrix for x, y, z body fixed Euler angles. The formula is given this. We have discussed this earlier. So for example, R11 is cos theta 2 cos theta 3, R33 is cos theta 1 cos theta 2, and so on. So C2 is cos theta 2, S3 is sin theta 3, and so on. We have discussed this earlier. So if you substitute t equals 0 in these expressions, theta 1, theta 2, and theta 3, and then if you compute cos theta 2, cos theta 3, or sin theta 3, cos theta 1, all the elements of this rotation matrix, you will get this rotation matrix. Okay, so R11 is 0.979, R23 is minus 0.172. So all these numbers are obtained by nothing but substituting t equals 0 in these expressions for theta 1, theta 2, and theta 3, and then evaluating sine and cosine of these theta angles. We can also plot, okay, each one of these components. So the position vector of in the A coordinate system can be given by these plots. So the plots are of the X component, which is blue, red, which is the Y component, and yellow is the Z component. So you can see that these plots we can get. Similarly, the space fixed angular velocity vector has three components, again X, Y, and Z. Again, we can plot this. The blue is the X component, this slightly reddish yellow is the Y component, and yellow is the Z component. We can also plot the magnitude, which is nothing but the X square plus Y square plus Z square. Okay, the square of the three component and then square root. We can also evaluate A alpha B, which is the acceleration. Okay, tangential acceleration. Alpha is the derivative of the angular velocity vector, and again we can plot it. We can also plot all the terms of the acceleration vector. So the acceleration of the origin is again given by this. The tangential acceleration can also be obtained, and it looks like this. Again, all the three components can be plotted, and also the magnitude can be plotted. The centripetal acceleration looks like this. The acceleration of the point P in the B coordinate system is given by this form. So the basic idea is, it is nothing very deep, that we have some way of computing each and every term of the linear and angular velocity and linear and angular acceleration of a point in a rigid body which is both rotating and translating. Okay. Let's take a different approach now, a slightly more interesting thing than just cooking up numbers and giving some numerical results. Okay, so the picture here shows a sketch of the Earth. So basically what we have is, we pick a point on the Earth, let's say this point. This is at a latitude of 40 degrees north. Okay, so this is in the northern hemisphere. So one standard way to assign a coordinate system on this Earth, rotating Earth, is that the x-axis is along the east direction, y-axis is along the north direction, and z-axis is the local vertical. Okay, so again they form a right-handed coordinate system. This is the center of the Earth. This angle is the latitude angle. The Earth is spinning with some omega, okay, angular velocity. And what we want to look at is, we want to see what are the various components of acceleration of a point which is on the surface of the Earth at a latitude of 40 degrees. So you can do it for any other latitude also. So the angular velocity is given by omega, which is 0 cos theta sine theta. So this theta is this angle. Okay, this is theta. And the linear velocity of a point on this surface of the Earth can have three components. It can be along the east direction, it can be along the north direction, and it can be along the upward direction. Okay, so z is u. So this can be three components. So what is the typical value of v? Let's assume that this is 100 meters per second. So it's a very large, some particle of air or some object is moving on the surface of the Earth at 100 meters per second. Okay, the angular velocity of the Earth is measured. It is very well known. It is 7.292 into 10 minus 5 per second. Okay, radians per second. So this is obtained from various literature is there. In fact, some of these things are obtained from this Wikipedia. So if you are given these numbers, v is this, omega is this, the latitude is 40 degrees, then we can find what is the Coriolis component. The Coriolis component is nothing but 2 omega cross v sine phi. Okay, so this sine phi is coming because of this latitude. which is very similar to omega cross V rel. Okay, and it turns out this is, if you compute this number, it is 9.374 into 10 minus 3 meters per second square. The interesting observation is that this is multiplied by sine of this phi. So where phi is this latitude. Okay, so when phi is 0, okay, then there is no Coriolis component. So there is no Coriolis component at the equator, and the maximum Coriolis component is at the poles where phi is 90. We can also calculate what is the centripetal acceleration of this point on the surface of the Earth. So now we need to know what is the radius of the Earth. It is given by 6.371 into 10 to the power 6 meters. Omega is the same as earlier, and the maximum centripetal acceleration is omega square r max, which is nothing but omega square r. Why are we saying r max? Because the radius of the Earth is maximum at the equator. At the poles it is slightly smaller. Okay, so this is at the equator, we will get this 0.03387 meters per second square. How much? So which one is larger? This is 10 minus 3. Okay, whereas this is 0.03387. So the centripetal acceleration is like 3.3 into 10 minus 2, whereas this is 9.4 into 10 minus 3. Okay, so the centripetal acceleration is larger. Let's look at Coriolis acceleration a little bit more. So think of the Earth. Okay, so the warm air is rising in the equator, and as it moves towards the pole, why would it move toward the pole? Because it is colder there. So the warm air will go towards the colder location. So it is deflected to the right in the northern hemisphere, and cold air coming from the north is deflected to the left. So this is the effect of the Coriolis component. So we have omega cross V, so omega is pointing outwards, V is pointing this way, and then it will move to the right. So why is it to the right? Because there is a minus sign. Okay, the situation is reverse in the southern hemisphere. So if you have a warm air which is going towards the south pole, the Coriolis effect will tend to make it in this direction, and cold air which is coming from the polar region to the equatorial region will move towards the left. Another very strong effect or interesting effect of Coriolis acceleration is that if you look at cyclones in the northern hemisphere, the cyclone will spin in the counterclockwise direction. Okay, and it spins in the clockwise direction in the southern hemisphere. So this is a cyclone which hit India in 2020. This name was Amphan. So this is a picture of that cyclone very close to the Indian coastline. Okay, and you can see it is rotating in a counterclockwise direction. Not showing here, but there are pictures of cyclones in the southern hemisphere which rotate in the opposite direction. The Coriolis acceleration is also very important to calculate the trajectory of a missile. So you can think of a missile being launched from one point on the Earth and it is supposed to go somewhere else. Okay, because the Earth is spinning and there is a velocity component of this missile, linear velocity, so there will be a 2 omega cross V. Okay, there will be a Coriolis acceleration, and because of this Coriolis acceleration, the path or the trajectory of the missile will deviate a little bit. Okay, so if there were no Coriolis acceleration, it will go and hit somewhere else. But due to the Coriolis acceleration, it will move to the left or right, depending on which way it is moving. Let's change topics. We would like now to discuss how to measure angular velocity and acceleration of a rigid body. Okay. So there are various ways to measure angular velocity and acceleration of a rigid body. I want to discuss something which is called as a MEMS gyroscope. So basically, a MEMS gyroscope is a very small device. In fact, it is so small that it fits into your mobile phone nowadays. So the main components are, there is a resonating mass, okay, and this mass can be driven up and down in this direction, okay, by means of some drive, by means of some actuator. And while it is moving, this mass, it has these springs which are attached so that it doesn't go and hit the support. And there are a fixed frame and there is a moving frame. On both of these frames, they have these fingers. Okay, so these are called sense fingers. So basically, there is a charge between these two fingers, and the distance between these two fingers, if they change, the capacitance will change, and you can measure the change in capacitance. So now let's see what is happening when this MEMS gyroscope is being used. So I have a oscillating mass which is moving up and down, and now if I put it on a surface which is rotating, so that means there is an omega. So let's assume that the omega vector is coming out of the page. Okay, so we have an omega here, and then there is a v relative here. So due to this omega cross v relative, there will be a sideways force, okay, which is Coriolis. So remember, omega cross v, right hand rule, it will move to the left or right depending on what is the direction of the velocity vector. And as it moves to the left or right, the distance between these two fingers will change. Okay, and you can sense the change in capacitance. And these springs make sure that you don't move too much. Okay, that it doesn't oscillate too much to the left or right. Okay, so basically measuring the capacitance change, I can find out what is the Coriolis effect. So I can find out what is the Coriolis component of the acceleration. So it is 2 omega cross v rel. I know what is v rel, and I know what is 2 omega cross v rel. So hence, from the change in capacitance, so hence I can estimate omega. Okay. So as the sense fingers move sideways, the change in capacitance can be measured at the sense fingers, and the change in capacitance is proportional to the angular velocity along one direction. Which direction? Perpendicular to this page. So if you have 3 such devices mounted in 3 perpendicular directions, so you can measure the 3 components of the angular velocity vector. Okay, and this is what is used in many gyroscopes nowadays. This is a very small device, and it is so small it can fit into a mobile phone. So in your mobile phone, in some good mobile phones, you can measure what is the angular velocity of the phone. Okay, and this is something which is used in many devices. We can also measure the acceleration of a particle or of a rigid body in 3D space. Again, the idea is that we want to use the change in capacitance when a mass moves, and attached to this mass there are these fingers. Okay, so there is one set of fixed plates and then one which is moving plate. So if you apply an acceleration, the distance between these two fingers, for example, here has changed. Okay, so hence the capacitance between these two will be different than what it was earlier. And these things here, they are like springs which make sure that you don't go too much. Okay, so by measuring the capacitance between these two fingers, so between this and this and between this and this, I can sense what is the acceleration, what is the direction, and what is the magnitude. Okay, so this is basically whatever I said is listed here. The acceleration along the axis causes the mass to deflect. Deflection brings capacitance change between the mass and the plate, resulting in a sensor output. The springs will bring back the mass when the acceleration is not present. And if you have three such accelerometers mounted in three perpendicular directions, we can get the three components of the acceleration. So we cooked up or rigged up a device in which we can measure acceleration and also the angular velocities. So this is a setup which was done in the lab. It consists of an Arduino Mega 2560 microcontroller board. Okay, it's a small microcontroller which is very commonly available in many labs nowadays. There is also a sensor which is called MPU 6050. Okay, it's a 6-axis movement tracker. It consists of 3-axis gyroscope, a 3-axis accelerometer, and some processor, because we need to process the signal to find out what is the angular velocity and the acceleration. So it is connected to this Arduino and microcontroller using some I2C bus. Okay, so let's not worry about the details, but it's a small device which is readily available, both this Arduino and this MPU 6050 sensor. Okay, so this MPU 6050 is a 3-axis gyroscope that uses MEMS device. Okay, it is using something very similar to what I showed in the previous slide. So due to the rotation of the gyro, the sense axis, the Coriolis effect creates a vibration which is sensed by a MEMS system within this MPU 6050. Okay, the acceleration along the axis causes the mass to deflect. This deflection brings capacitance change between the mass and plates, and again it results in a sensor output. So all these signals are then amplified, demodulated, filtered, and finally it generates a voltage proportional to the angular rate and linear acceleration. This device is sometimes called as an IMU. Okay, it is very commonly seen in many phones and various other places. It's also called inertial measurement unit, and it can measure acceleration, angular rate, and orientation. Okay, some of these IMUs sometimes also comes with a magnetometer, basically to find out which is the north direction. So here are the hardware which was done by one of the TAs of this course, Pramod Pal. So basically this is the Atmega Arduino board. There are some processors. This is the sensor. This is the MPU 6050 module, and you connect it up. Okay, let's not worry about the details of connection, but it is very straightforward and simple. And then this is showing the hardware diagram, and this is also showing how to connect this MPU 6050 to the Arduino board, which input of the Arduino board is connected to which output and so on. So some ground is there, some VCC is there, and so on. So here is a video which shows how this combination of MPU 5060 and this Arduino can be used to measure orientation. Okay, so this is a video which I'm going to show you, which shows how to rotate about x-axis. So I will rotate this breadboard about the x-axis, and then I'll show you what is the output. Okay, so Pramod is rotating this breadboard with the sensor. So there is some angular orientation, okay, some angular velocity, and as you saw here, it shows what happens to the plot of this angular velocity as a function of time. So once it is stationary, it comes down to 0. This is the same thing I'm going to rotate now about the y-axis. So this is the y-axis, this is the x-axis. Now we'll rotate about the y-axis. So at t equals 0, nothing is moving. So it is at 0. Okay, the angular velocity is 0. So as you rotate about the y-axis, you can see this plot or the output of this sensor, and it shows how the angular velocity along the y-axis is changing. So as you can see, there was some jerk, okay, while moving up and down, jerk. That is faithfully captured in this output. Here is a demonstration of rotation about the z-axis. Okay, so as you can see, he rotated by some amount, and then it came back about 90 degrees, and then it went to 90 degrees and it came to 0. So we can show all these angles and rotations by this simple microcontroller, Arduino board and this device. This is a demonstration of acceleration. Okay, so again, this is the same Arduino board. It is the same MPU 5060, and the acceleration data is a little bit noisier. As you can see, this is some small value is there. So this value is nothing but 9.8. Okay. And what he is going to show you is that he will lift it to some level and drop it. So while it is being dropped, okay, what it should come back, we should measure this 9.8 G, which is basically what is being measured. So hence, at normal thing, it is like 9.8, and when it is falling freely, you can see that it is very close to 0. Once we know what is the acceleration by this device, can we calculate position of this device? Because eventually we would like to have position, velocity, and acceleration linear components. Okay, so it turns out that it is very hard. It is not so easy to calculate or compute the position of this object if I know the acceleration. And the basic problem is that we need to integrate acceleration twice to obtain position, and we do not know the initial conditions. Okay, so simple calculus, if I know acceleration, if you integrate once, we will get velocity, but then you have an integration constant, which is C1. Then when you integrate it again, you will have another integration constant, which is C2, and the C1 will become C1 into T. Okay, but we don't know C1 and C2 very well. Okay, so the incorrect initial conditions will result in errors, and these errors will increase with time, because if I do not know C1, remember C1 is multiplied with T. Okay, so if C1 there is an error, then as time progresses, C12 will keep on increasing, the error will increase. We also need to subtract gravity from the acceleration measurement by the IMU. So this is a bias. And if this is also not done correctly, the errors will pile up. So measuring position from accelerometer or from acceleration is non-trivial. It requires sophisticated algorithms. And there's a whole field of using algorithms and using processes and techniques such as Kalman filters, which can be used to obtain the position from acceleration readings. Okay, it is not impossible. Very, very accurate estimation of position and orientation is possible, and it is used in many missiles and various other devices, okay, and systems. The position can also be measured using GPS. So nowadays, GPS is available all over the world. Okay, so you can, from your mobile phone, you know exactly where you are. Okay, but it is not very useful for small mechanical systems. So if you have a small robot or if you have some small mechanical system and you want to find out what is the position of some part as this mechanical system is moving, GPS is not very useful. The IMU which I showed you can be used provided you do it properly and you can estimate the position and orientation correctly. So in summary, the linear velocity is the derivative of a chosen point on the rigid body. Okay, so the angular velocity is not the derivative of three orientation parameters. So if you had x, y, z Euler angles and say let's say theta 1 about x, theta 2 about y, theta 3 about z. So the three parameters are theta 1, theta 2, theta 3. The angular velocity is not simply theta 1 dot, theta 2 dot, theta 3 dot. Okay, we need to obtain the derivative of a rotation matrix. We will get a resulting skew-symmetric matrix, and from that we can obtain the angular velocity. There are two kinds of angular velocities. One is the space fixed and one is body fixed. Both are related to through the rotation matrix. The position and orientation can be estimated by integration of linear and angular velocity. The angular and linear acceleration is the derivative of the angular and linear velocity. The effect of the Coriolis component resulting from the rotation of the Earth is seen in many atmospheric phenomena. Okay, it is seen in cyclones and it is also seen in motion of a missile. And we also have nowadays very simple and cheap IMUs, okay, inertial measurement unit. So these are basically MEMS gyroscope and accelerometers which can be used to measure angular rates and linear acceleration, and then using some reasonably sophisticated algorithms you can find the position of a rigid body in 3D space and the orientation of a rigid body in 3D space. So in this lecture, we looked at position and orientation of a rigid body in 3D space, the linear and angular velocities and acceleration. In the next lecture, we'll look at multi-body dynamical systems.